In this section, we're going to be describing what happens when you have the chain rule as it applies to functions of multiple variables. So first off, if you will kindly recall with me, the chain rule from back in Calc 1. So the chain rule worked on compositions of functions. If y is equal to some function of u, and then u is equal to some function of x, which means that y is equal to f of g of x, definition of a composition, then the rate of change of y with respect to x is equal to, we figure out how changing x changes u, and then we figure out how that change in u has a change in y. And the way that it works is we differentiate y with respect to u, and we multiply by the derivative of u with respect to x. Y is the actual dependent variable here, and x is the actual independent variable. U just sort of acts as an intermediary. So y is a function of u, and then u is a function of x. So we have the dependent variable, we have the independent variable, and u I tend to refer to as the intermediate variable, or intermediary variable. Sort of like a catalyst for a chemical reaction. It is involved and it speeds up the process, but it's not 100% necessary to have it there in order for us to produce a reaction. Now, as it applies to multiple variables, so new stuff. Suppose that z is a function of x and y, but then x is going to be parameterized in terms of t, and y is going to be parameterized in terms of t as well. So essentially we're defining x and y parametrically, and then we're plugging those into some function that we're referring to as z. Now the idea is z is now a function of both x and y. X and y are both functions of t. So we have our dependent variable z, we have our independent variable t, and then we have our intermediate variables x and y. I would also like to have you recall from the previous section the subject of differentials. When we were calculating the total differential of z, we said let's take the partial derivative of z with respect to x and multiply by the differential of x. Then take the partial derivative of z with respect to y and multiply by the total differential of y. So when we make an alteration to either x or y, it's going to have an impact on z. Well here, if we make an alteration to t, the alteration to t is going to have an impact on both x and y, and then both x and y are going to have an impact on z. So the way that this chain rule works is, if I take dz dt, this is going to be equal to the partial derivative of z with respect to x times the exact derivative, or the ordinary derivative, of x with respect to t. Additionally, we'll also have the partial derivative of z with respect to y times the ordinary derivative of y with respect to t. Now the way that I tend to remember this is based off of this thing over here, and this is referred to as a tree diagram. A tree diagram is a great way to keep track of when z is a function of multiple variables, and then those multiple variables are functions of multiple variables as well. This tree diagram says z is a function of what variables, and then these variables are a function of what variables. The way that you construct this chain rule is by using the following. From basic counting techniques, there are two ways to count things, and they will involve an or and an and. Anytime you say or, we're referring to addition. Anytime I say and, I'm referring to multiplication. How many ways can I get from a z to a t? Well, I can go from z to x and x to t, z to x and x to t, or I can go from z to y and y to t, z to y and y to t. This is going to work for the more general cases that we're going to see in the future, but this is a great way for us to start the process.